All right, Chapter 5, review quadratic functions, and this is the calculator section. So you're allowed to use a graphing calculator. I would suggest it for most of these. You don't have to, but you could. So let's just jump right into it. So the first one, number 1, says the power P and horsepower generated by a high-performance speedboat operates at R revolutions per minute can be modeled by this equation. So basically what this is saying is you can figure out the horsepower if you input a certain RPMs, revolutions per minute. And just by looking at this, it's a quadratic because it has an R squared in it, and it's negative. So I know that this thing is going to have some sort of a curve. Kind of looks like this. And basically I'm trying to find, it says part A, what is the maximum power? So this part right here represents the power. So I'm trying to find the Y value, the maximum Y value of the vertex there, and then how many revolutions per minute achieves this power. So that's going to be the X portion. So basically I got to find the vertex. So let's punch this into my graphing calculator, and I might already have this one put in from class, but we can double check. There we go. I'll turn him on. So Y equals, yep, so this first one's in here. I had to play with the window a little bit. You can use Zoom Fit if you'd like. You could also use the table, and I'll show you here in some later problems. But since this one's already here, we're just going to take a look at it. So I got my picture, I got my graph, and I found a nice view. Just for reference, my window here was 0 to 10,000 for the RPMs, and then my horsepower went from 0 to 500. And it took a little bit of playing around to get that spot. But so once I have my graph, I'm going to use the calculate feature. And I'm going to calculate the maximum. So I go second, trace, which is the calculate menu. And we're going to find the max, which is number 4. And what I need to do is I need to click a spot on the left side and the right side of the max. So right there you can see the X on the left side. I'm going to go over. I'm going to click somewhere past the maximum to the right of it. Do you want to guess? Yes. And then I look and I see my answers there. So the X coordinate, which is the R in this equation, my revolutions per minute is about 6122. And it says go to the nearest horsepower. So we're going to go 60. Come on now. Give me my calculator back. Oh, somehow every time I go to click on my, well, it's gone, but it's going to be 6122, and I wish I could find a way to make that stay up there while I'm doing it. Maybe I'll have to move it to the side. But my revolutions per minute was 300. My Y value is 300. So 6122 and 300. Oh, there we go. So these were RPMs, and this was horsepower. All right, let's move on to the next one. So scrolling down, slide this over just a tad. So number 2, path of a soccer ball is modeled by that equation. X is the horizontal distance, and H is going to be the height. So if you know the horizontal distance, you can input it in. You can figure out the height. So you could also kind of think about this just as like a little chart if you wanted to. And you could say, well, maybe I'll do this over here. You could say the horizontal distance versus the height. And then you could just kind of think about plotting some points. So like when you went, these are meters. If you go 1 meter horizontally, it'll tell you what height it is. 10 meters horizontally, it'll tell you what height it is. So this one's not a time function. It's a horizontal distance compared to vertical distance. But we're going to put this in our calculator. So let's pull it up and let's go to a new Y equals. Clear this one out. Negative 3.125x squared plus 0.25x. And hit enter. Now, I'm probably not going to get lucky, and let's just hit graph and see what happens. And basically, I'm not seeing anything. It didn't even show up. So what I might want to do is I might want to go to the table. So I'm going to go second table. And this has numbers from the last question. So I want to go back and start my x's at 0 and go by ones. So I'm going to do table set, second window. And let's just start at 0. And let's go the table by ones. And now let's just go back to the table and see what's going on. So remember, our x value is the horizontal distance. So I can see my height in the y column getting bigger. But it's going pretty slow. You know, I'm all the way up to, say, let's just stop. I'm all the way up to 50 feet. And, oh, it came back down to the ground. So it looks like there was a maximum in there somewhere. So just looking at my table, where do the y values get the highest? It looks like we're getting bigger. Oh, we just came back down. So if you can notice rate, it looks like about here. Somewhere around 25 horizontal meters, I'm at a height of 3.125. And then you kind of see how it's the same on both sides. So this one I almost don't even have to do the graph, because if you look at that 3.125, our points are symmetrical on both sides. You have 3.12, 3.12, 3105, 3105. So that tells me that that is the exact maximum there. So at what horizontal distance does the ball reach the max height? What is the max height? So we're going to have a max height 3.125 at 25. So we have 3.125. And that happened when we were at 25 meters out. So basically you booted the soccer ball, and 3 meters is about 10 foot high, so it didn't go super high. At what horizontal distance does the ball hit the ground? All right. So this is basically saying, you know, at what x value the ball hits the ground at y equals 0. So I want to keep going, and so I'm not even using the actual graph. I'm just using the table for this one. So let's just go, and I think we saw it a minute ago. And actually, I shouldn't even have to do what I'm doing, so I'll explain in a second. But it looks like it's at 50 meters. So at 50 meters, we hit the ground. Now, I really should have knew that already, and I'll kind of show you why. Because if you think about your graph, this thing goes up and it comes down. Well, the maximum point was at 25. And we were over here at 3.125. Well, the maximum is always going to occur at the halfway point. So if we started at 0 and we went to 25, I kind of knew it was going to be 50, even without checking my table. So that's just kind of another little bonus fact you can use there. All right, number 3, the old spittlebug, the world's highest jumping animal relative to its body length. So let me pull up my graphing calculator, and I'm going to move him over on this one to the other side. It's kind of hard doing this screen, messing with this calculator, but we need it, so we got to do it. So let's go back to y equal, clear it out. So we're talking about the height. So our y value is the height, and our x value are our seconds. So we got height and time. I like those ones, pretty straightforward usually. Negative 4,000 t squared plus 3,000 t. There's no initial height, so it must be 0. The bug is jumping off the ground, so we have a 0. And so we're trying to figure out, again, the max height, so the top of the parabola. And then we have a ratio thing here we got to calculate. So we'll worry about that once we get A. So let's check out A. So let's graph this thing. Let's go to graph, see what happens. Enter graph. And I have no idea how high this thing can jump. It's in millimeters, so it's going to be kind of weird. All right, so I didn't see the graph there. And I'm going to go and I'm going to peek at, I guess I'll go to the table. Well, kind of had some luck with that last time. Or actually, let's try the zoom fit. I haven't tried that yet. So let's go to zoom fit. I forget which number it is. If you use it enough, you can just hit the number. So it's 0. Oh, I don't really like that. So I kind of see part of it. I kind of see like the right side. But it looks like my window needs to go up and to the left some. So if I go to my window, oh my goodness, 0 to 10,000. So I think I need to see more negatives. So let's go like, I don't know, let's go to like negative, I don't know. Let's go to negative 10,000. I'm just kind of guessing here. Well, that doesn't make sense. If x is time, let's just kind of use some common sense here. If he's jumping and we're talking seconds, this bug is not going to be off the ground very long. So we're going to go 0 to 10 seconds. See, zoom fit was just crazy. I don't even know why it did that. So we'll go by ones. Now, how high it jumps, well, I'm going to start on the ground. So I'm going to put my height on the ground. And if we're jumping, God, I don't know. Maybe I'll just go to 1,000 and see kind of what happens right there. Let's go to 1,000. I like to divide by 10, so I'm going to go by hundreds. See what that looks like. Oh, so my time was way too long. My x's went from 0 to 10. They only got to go to like 0 to 1. So let's change our window. 0 to 1. And I'll go by 0.1s. Enter. Ah, that's a nice looking graph. So we kind of zoned in on a window. Let's get the maximum height. So I'm going to second trace. Max is number 4. And I got to go to the left side. Left side first always. So left, enter. Right side, enter. Guess. Boom. So it looks like at 0.375 seconds, this thing has jumped 562. So 0.375 and 562. So at 0.375 seconds, we hit a max height of 562.5 what? Looks like millimeters. Not sure exactly how high that is. We could convert it. I think we got to convert it by doing like 0.254, and that would change it into inches. But we answered the question. What is the ratio of the spittlebug's max jumping height to its body length? So a ratio is a fraction, or you kind of do like a dot dot. I'm going to do a fraction. The max jumping height, all right, so 562.5, compared to its body length, that goes in the bottom, which it said the body length was 6. So when I ratio that out, and I divide that, 562.5 divided by 6. So 560, well, I got to get out of there. Quit. 562.5 divided by 6 equals 93.75. So that spittlebug can jump 93.75 times the length of its body, which is pretty crazy. So if a human could do that, if I'm 6 feet tall, I'm not, I'm like 5'11". But if I could jump like that, so it says in the bottom one, the best human jumpers have a ratio of 1.38, meaning the best jumpers we have can jump at a height 1.38 times their height. But what if somebody who's 1.8 meters, which is 5'11", jump if they were a spittlebug? So we'd have to do 1.8 times 93.75. 1.8 times 93.75. So I'm going to just hit times 1.8. 168.75 meters. Wow. So if we were a spittlebug, we would basically be, that's like, a football field's 100 yards, which is a little bit less than 100 meters. So, it'd be like a football field and a half. We'd be jumping a long ways. I know I'm kind of being lazy on that part, but it's not really part of the question, so not going to go into what if world. Number 4, baseball is thrown with a vertical velocity of 50. So you'll notice that's the initial velocity in my equation. So this 50 is basically just this number. Initial height, so we're throwing from 6 feet high. And T is the time in seconds, H is the height of the ball. So how many seconds does it take to reach its maximum height? What is the maximum height? So again, we're just trying to find the vertex. These numbers look a little friendlier, so hopefully when I do my graphing calculator, it won't be so hard. So let's talk about our window before I even put this thing in. T is the time in seconds. So if I throw a baseball, it's definitely not going to go longer than 10 seconds. Probably even much shorter than that, but we'll go 0 to 10 seconds. How high am I going to throw this baseball? I don't know. Let's just do 100 feet just to be safe. Go by tens. Let's go to y equals and graph this thing. Clear. Negative 16x squared plus 50x plus 6. Enter. Nice little graph. So it looks like it only was in the air a little longer than 3 seconds. And I really didn't get anywhere close to 100 feet. If I wanted to change my window and make it pretty, I could. But if I want to just get the maximum, I think I can do it right now. Second, calc, max is number 4. Left bound. So right now I'm at x equals 5. So I got to move way to the left. So I'm going to keep going left, 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 left. Hold that down. There we are. So there's the first one to the left. There's to the right. Guess. So at 1.56 seconds, I am at about 45 feet. 1.56, 45 feet. So something you want to do kind of before the problem starts, and I could make that 0.06, but you may want to just talk about what your x and y is, just so you kind of know. And x in this problem is really t, and h is really y. But it may be helpful for you in the very beginning to kind of really express what those are so that you know what those numbers represent over on the side. Number 5, shooting an arrow in the air. So we got a lot of parts to this. So how long is it in the air? So that's going to be my t value before it hits the ground. When does it hit the ground? Max height. So now I want to know all the pieces. Highest point, the time, and then when it hits the ground and the time. So let's get our graphing calculator back up here. And we'll move him over this side. Go to y equals. The negative 16 can stay. Actually, I'm just going to clear it out. It takes longer for me to monkey with it. Negative 16x squared plus 63x added to 4. Boom. Lock it in. Talking about my window, well, let's just see if we get lucky. Let's just graph it, see if we get lucky. Oh, not too bad. So it looks like roughly just ballpark. It's in the air for about 4 seconds. And it looks like at 2 seconds, it's at the highest point. I could do this using algebra. Like if I really wanted to, I could find the vertex and I could find the zeros using algebra. But I don't want to. I have a graphing calculator, so why not just use it? So let's do some calculating here. For the max, I think my window's okay. So let's calculate the max. So second calc 4. And right now you can see that I'm at x equals 5. And so I'm way too far to the right. So I'm going to actually move this to the left. And now we're coming back. There we go. So enter. And let's go to the right side. Enter. Guess. So at 1.97 seconds, we're at about 66 feet. So let's just kind of write that in. So I just answered part C and D. So at 1.97 seconds, we went to 66 feet. So this is dealing with the vertex. Now we got to go over and find the 0 to see when it hits the ground. Something you're going to have to kind of do on this part is, in order to calculate that 0, I mean, one, I could look at a table, but since my x's are getting into way down into the hundredths of a second, I don't really feel like doing all that. So what I'm going to do is I'm going to adjust my window, and I'm going to just be sure to go underground some. So I'm going to go to y min of let's say -50 and regraph it. So now I can see it go underground. And now I can calculate that 0. So I'm going to go second calc. And 0 is number 2. And again, I got to go to the left and the right side of the 0. Right now I'm at 5. I don't know why it keeps going to 5, but now I'm on the left side of the 0. Hit enter. Go below the line to the right side of the 0. Hit enter. Guesstimate it. So it looks like it's exactly 4 seconds. I'm at 0. So it looks like that calc function could be a little bit off, in my opinion, because if it said it hits the ground at 4 seconds, and which I guess A and B are kind of the same question. When does it hit the ground? How long is it in the air? I think these two are pretty much the same. But if it's 0 at 4, then my max height should be exactly at 2. So I'm a little bit perplexed as to why it calculated 1.97. Maybe it's rounding at some point. The only way to know for sure, and I am going to do this just for the heck of it, I'm going to go check out my table. Second table set. And I'm going to start my table right at 1.9, let's say. And I want to go by 0.01s. I want to really get down to the nitty gritty. So let's go second table. And let's just see what's going on here. Second table. Second table. There we go. So I can see my height getting bigger. Still getting bigger at 0.016, 0.014. So it looks like that max height was legit. 1.97 is the max, is the time of the max height. So it looks like the 0, they just kind of guesstimated. Although I want to look at it. So second table set. Let's skip forward to 3.99 and just kind of zoom there. And yeah, it must just be a rounding thing. I'm not sure, because that doesn't make 100% sense to me, but we're just talking about hundredths of a second, so it's not that critical. All right. Which one are we on here? Number 6. Hypotenuse of a right triangle is 2 centimeters longer than one leg and 4 than the other leg. All right, so let's I haven't done this problem before, so let's see what we got going here. So I have a right triangle. And the hypotenuse is 2 longer than one leg and 4 longer than the other leg. So if the hypotenuse is 2 longer than one leg, all right, so let's just say this is Well, there's a couple different ways how I could set it up. Let's do the shortest leg. So the shortest leg, let's call, well, I could call him x, but then when I solve for x, it won't be the shortest leg. So it says let x represent the hypotenuse. So I guess I have to do that. So if I'm 2 bigger than one of them, this one is going to be x take away 2. So now my hypotenuse is 2 bigger than him. And then my hypotenuse is 4 bigger than the other. So this will be the hypotenuse take away 4. So that's kind of your first part. Well, now I got to use Pythagorean theorem to solve this thing. So man, this is going to be a little bit of work. So x minus 2 squared plus x minus 4 squared. Remember, leg squared plus leg squared equals hypotenuse squared. And I got to do some algebra here. I got to do some work. So let's grind this thing out. So this would be x squared minus 4x plus 4 plus x squared minus 8x plus 16. So far all I did was I did this part here, and I did this part here. And then the right side is just equals x squared. And so when I gather up all my like terms, I'm going to kind of move up top over here where I got a little more room. 2x squared minus 12x's, so I gather these dudes together, plus 20 equals x squared. Well, normally when I solve these, I want to set one side equal to 0. So I'm going to subtract x squared from both sides. So I'm going to get x squared minus 12x plus 20. I'm always going to try to factor first. Don't know if it's possible, but let's see. You know, I got 1 and 20, 2 and 10. Ooh, I think I can get it with 2 and 10. I think that right there will get this for me. So I have x minus 2 and x minus 10 equals 0. So use zero product property, ZPP. This parenthesis is 0 when x equals 2, and this one, x equals 10. So find the solutions for part A. I have them. X equals 2, x equals 10. Are both solutions reasonable in the context of the problem? I don't believe x equals 2 is reasonable, because if I plug 2 in, that's going to make this side have a length of negative 2. And if I plug 2 in here, it'll make that side have a length of 0, which we don't have a triangle. So I think 10 is the correct answer. And if I plug this in, 10 take away 4 would give me a side length of 6. 10 minus 2 would be a side length of 8. And this would be 10. And 6, 8, 10 is a Pythagorean triple. All right, number 7, looks like we got a volleyball. Picture here says a player bumps a volleyball with an initial velocity of 20 feet per second. Write a function h in standard form for the ball's height in feet in terms of time t. And so it looks like at 4 foot, that's our initial height, and then we're trying to figure out how high it goes with that beautiful image there. So let's get after it. So we need to write our function. So this one, they don't actually give it to me, so I'm going to just say, okay, h of t equals gravity on Earth in terms of feet. So that's always there. The initial velocity comes next. So our initial velocity is plus 20t. And then the initial height was 4. So all numbers are accounted for. So just remember, this is the initial height. This is the initial velocity. And this is the gravity part. All right. So now what is the height of the ball? So we need to figure out the vertex there. So I'm going to use a graphing calculator for this one. Why not? Been using it all along. So let's do this. Turn it on. Y equals, let's just clear that out, negative 16 x squared plus 20x. Takes a lot longer punching it on this big board than it does to just do it in my hand. plus height of 4, enter. So let's think real time about this problem. We're going to go 0 to, I doubt if it's going to be in the air, 10 seconds. Maybe we'll shrink 0 to 5 seconds. And then for the height, let's go from, and I didn't even check to see if we needed to know when it hit the ground. So if I need to go negative, but I'll just go 0 to, I don't know, 25, 0 to 25 feet. That'd be an awful high volleyball hit, but yeah, maybe we'll go by 2s. Let's just see what shakes out. Oh, not up in the air very long, so I could have shortened my time. Maybe I'll do that. Maybe I'll shorten it to 2 seconds. And we'll go by halves. All right, that looks a little smoother. And we are trying to find, let me move this out of the way here. So we are trying to find, so I wrote the function, that was part A. What is the height of the ball? So let's calculate the maximum there, which is number 4. And I need a left bound first. So left side, enter. Right side, enter. And guess. Maximum is 10.25. So we have 10.25 feet. Our equation, guess I'll write it again, was h of t. And suppose the volleyball were hit under the same conditions, but with a stronger velocity. So instead of 20, we want to change this number right here, and we want to change that to 32, and see how that's going to change things. So let me come over here, and I'm going to change this to 32. So delete, and I'm just going to retype it, 32x plus 4, and let's get the new maximum height. Still fit in the picture, but a lot higher. So let's recalculate. Second calc. Oh, I don't know what happened there. Second calculate, maximum, left side. Hopefully you're starting to get the hang of how this works. Enter. Looks like 20. All right, so this one goes, instead of 10.25, this one goes all the way up to 20 feet. So, but that doesn't answer the question, because it said how much higher. So I would have to subtract those two. I'd have to do 20, take away 10.25, which is 9.75 feet. So an SAT question, they would probably have the 20 in there as an answer to try to trick you, which is kind of mean, but that's what they do. All right, number 8. Player throws a ball straight up towards the roof of an indoor baseball stadium. The height after t seconds. The height of the roof is 208. Will the ball hit the roof? Why or why not? So I got gravity. So let's kind of go in here and just see what's going on. So I have gravity right there. I have the initial velocity right there. This equation, I want to know, is it ever going to get to 208? Like, is it ever going to cross that line there? Couple different things I could do. I'm going to show you a little bit different way to do this one. You know, if you knew it was going to hit the roof and you wanted to know what time it's going to hit the roof, you could put 208 here and solve that and say, well, hey, what t is going to get me to 208? But we don't even know if it's gonna. So I could put the equation in the calculator and just find the max and see if it's higher than 208. That might be one thing. I'm going to show you a little different way just to give you another option. You could put this equation in the calculator And then you could come back and put the horizontal line, y equals 208, and then see if it actually gets that high, if it hits the line or not. If it doesn't intersect that line, then it's not going to hit it. And I think that should be that's 112. All right, so let's get my calculator up. Where are we? Boom. So let's pop this guy in. Negative 16x squared plus 112t. And then just hit enter. And then I'm going to enter the second line, just y equals 208. Just a straight horizontal line. Now, I better change my window because I know in the last problem we only went to 25. So let's go from, we're throwing a ball, so we'll keep it under 10 seconds. Go by ones. And then we need to go to at least like 250 to see if it goes that high. Maybe we'll go by 25s. And let's graph it. So there's the ball. Ooh, there's the roof. We never hit it. So this one fell a little bit short. And if I wanted to, I could go to my table and I could check things out. But it looks like it stopped short. So I'm going to answer this question and say no. No. And I could say something like it doesn't intersect y equals 208. Or, maybe I actually work it out and I tell what the max is and I say, no, the max is 190 or whatever. I'm not going to do it, but I know the answer is no. Suppose you have an anime drawing 9 inches wide by 12 inches long. So that's the actual drawing. And then you want to frame it with a frame that has an equal width all the way around. The area of the picture plus the frame is 180. So find the width. So I'm going to go off the screen a little bit on this one. So we have a little more room. So let's kind of draw this. So here's my drawing. It's 12 by 9. We then wrap a frame around it that's the same all the way around. So we have an X, we have an X, we have an X, we have an X. And I know that the black rectangle has an area of 180. All right, so the length times the width is 180. But I don't have dimensions, for this length and for this width. But what I can do is, I know that this is 12 plus x plus x. So I basically have 12 plus 2x. And then go in the other direction. I'm going to have 9 plus 2x. Because I got the border on each end. So I can kind of replace those two dimensions for my length and my width. And I'm going to have 12 plus 2x. 9 plus 2x, and that's got to shake out to be 180. So we FOIL it out, we expand, and we get 108 plus 24x plus another 18x plus 4x squared equals 180. So that's 108 plus 42x plus 4x squared equals 180. Now I can subtract 180 from both sides because I want to set this thing equal to 0. So subtract 180, subtract 180, and I get 0. And I'm going to write this in normal order. 4x squared, descending order, minus 72. So now I have a situation. Well, first of all, I see those are all even numbers. So maybe I'm going to come in here and just divide this side by 2 and this side by 2 to shrink it a little bit. So that's 2x squared plus 21x minus 36 equals 0. I don't think there's anything else I can pull out. So right now I have three options. Okay. Option number 1 is I could do bottoms up. All right. Option number 2, I could use quadratic formula. Option number 3 is I could graph and then use the calc feature to figure out the zero. I need to find the zero of this function. So I'll do it a couple different ways. So bottoms up, it's going to be x squared plus 21x minus 72 equals 0. How can I get 72? 1 and 72, 2 to 36, 3 goes in there, 24, and there it is. 3 and 24 will do it. Positive 24, negative 3. And then I often forget to do this. I have to now undo, up here where I multiply by that 2, I got to now divide by the 2. And that gives me, if I turn this into a decimal, 1.5 and 12. Now I got to find the zero product property. When is each parenthesis equal to 0? Well, it looks like x could be 1.5 or negative 12. Since I can't have a dimension of negative 12 as my width, it looks like 1.5 is going to be it. And if I check this, if I put 1.5 in, basically I'm going to have 9 plus 1.5 plus 1.5, so plus 3. So this is really going to be 12. And going the other way, it's going to be another 1.5 plus 12. So that's 12 plus 3 would be 15. And 15 times 12 is 180. So we're good to go. I'm not going to show the quadratic formula way because it's just long and I don't want to drag you through that. You could graph it and find the zeros. You guys have done that several times. But I could just go y equals and graph that thing right there, solve for the 0, and I would also get a 1.5. All right, number 10 says if a fitness center charges its members $300 per year to join, they get 1,000 members. For every $2 increase in price, they expect that they'll lose 5 members. So how far can they push that? How many times can they keep increasing that price to maximize revenue? And then what will be the max revenue? So revenue is how much money they bring in. So you have the number of members, which is 1,000, times the price, which is $300. So that means right now they're currently bringing in $300,000 per year. Now it says if they increase $2, so on the first increase, I'm going to kind of call this like, this is going to be my x's. This is at 0. This is where we are now. Well, after the first increase, that would put me at 302, but then I'm going to lose 5 members. So I'm going to be at 995. So let me bust out my calculator here really quick. And we are going to go 995 times 302. So that gives us 300,490. So we actually did better by charging a little bit more. And if we do it again, let's go up by another $2, which is our second increase. That'll be at 990. So 990 times 304 equals, we have even more, $300,960. So I've made almost 1,000 more by increasing the price $4. Now there is going to be a breaking point where your members start to drop enough to where even the increase in price, it's going to start working against you. So instead of just running this table and doing it over and over and over until we find the highest point, let's put this into an equation. So if you notice what we started with, we started with 1,000. And every time when you notice what we're doing each time, we are increasing by 5x, or decreasing, I mean. So we're subtracting 5 times, and x is just every single time we do an increase. And if you look at the 300 column, these are going up by 2x. So 300 plus 2x. So I was just kind of trying to show you another way where quadratics kind of come into play that isn't like your typical height projectile type problem. So what I could do right now, if I want to, I could actually enter this into the graphing calculator exactly how it is. All right? And I really don't need to expand it out. If I want to, I could expand it out. You know, I could do FOIL on this thing, and I would get 300,000. That's plus 2,000x. That's minus 1,500x. And minus 10x squared. You know, so normally we would write that as negative 10x squared, positive 500x, positive 300,000. And we want to try to find the max of that. So either one, you could punch either one into your calculator. I'm going to try the top one just because we've never graphed one like that. So I'm going to punch this in the calculator, see what shakes out. So graphing calculator. And we'll move him all the way over. So let's go to y equals. Looks like I gotta reset it really fast. Seems to be something I have to do every time I restart this up. All right, so we go to our grid, and I'm just going to type in parentheses 1,000 minus 5x parenthesis. Kind of the nice thing about doing this is if you make a mistake doing your expansion or multiplying it out, you know, this kind of takes out the chance of making a mistake. Just punch it in exactly how it is. All right, so let's hit graph. I'm not going to see anything. Actually, what's this error talking about? Let's quit. What I do? Oh, I think I put a negative sign instead of, doggone it, delete, insert, a subtraction sign. Let's see if I did it again over here too. Oh, that's a plus, so it doesn't matter. Actually, I'm not going to hit graph yet because I want to use some common sense here on the problem. So when I think about my x, you know, how many times can I do this iteration? Well, if I do it a certain number of times, I'm not going to have any members. So if I'm losing five members every time, if I do that 200 times, I'm going to have 0 members. So I know my x's really can't go anywhere. They got to be between 0 and 200. Otherwise, I go into negative member territory. The y's, you know, right now I'm at 300,000. It looks like we're going to increase and keep getting bigger, and then we're going to fall back down. So I don't know. Let's maybe investigate, see if we can get up to 500,000. That might be a little bit ambitious, but let's just see how far we can go. So I'm going to go second window. Oh, not there, just normal window. So 0 to 200. We'll go by 20s. I always like to find that range and divide it by 10. And then we're going to go from 300K, a lot of zeros, to 500K. And that's 200,000, so I'm going to go by 20,000s. And let's just graph it. Oh boy. So I was a little ambitious on my y's. We went from 300,000 to 500,000, and I think we went by 20,000s. So let's just go from like 3 to 320. So I'm not seeing much of a graph. So I'm not going to make $500,000 like I was hoping to. But we'll go to 320,000. So I need to change my scale. So now that's only a range of 20,000. So divide by that by 10. Let's go every 2,000. And let's just graph that. All right. Okay. So it looks like my x's really, I mean, right now I think I have enough to find my maximum. I could keep playing with the window to get it pretty. But let's just get in there and find the max. This video is getting kind of long anyway. So maximum, boom. Left bound, well, I'm at 100, so I'm going to have to go back a long ways. I don't know why it sets the left bound so far over. There we go. So hit enter. Then let's go to the right side. Enter. And do it. So it looks like at about 25 iterations, we get to 306,250. So when x is 25, so I'm going to kind of put this into perspective here. Do a little erasing. So it's looking like on my table, if I jump all the way down here to the 25th price increase, you know, if I put 25 in for both of these numbers, you know, that's looking like I raise my price up to $350. And 25 times 5, well, that's 1 1/4. So I'm going to lose 125 members. So I'm only going to have 875 members. And punch that in my calculator. 875 times 350. So it looks like $306,000, 250 with it, is about the most I'm going to squeeze out of that. You know, since it's a decimal, you can't really have a decimal amount of members. So let's just kind of go to our table and let's just verify what's going on here. So my table, we had x at 25, so I think I can just leave. Let's see what my table set is at. It's going 0 by 1s. Let's start at 20. Save ourselves a little bit of grinding. Yeah, so it looks like I'm getting more expensive, more expensive. Over in the Y column, I'm going bigger, bigger, more money, more money, more money. Oh, yeah, right there at 25. That's the peak. Because you see at each side, I have a 240 and a 240. 250 is the top. So did we answer the questions? How much did the gym charge to maximize its revenue? $350. What'll be the max? $306,250. All right. Let's get rid of this. Clear this out. And I think we got one more problem to go. The old Sky Deck. I don't know if you've ever been there in Chicago, but it's pretty cool. You're 1,353 feet high. You walk out on a glass floor and glass all around you, and it just feels like you're floating in air. It's pretty scary if you're afraid of heights. So the Sky Deck is 1,353 high. If a person could drop a penny from that height, A, how long would it be until it hits the ground? B, then they go into a speed equation. So let's do part 1. All right, so free fall basically is what this is. So our height, and I don't know if you hear that wind outside, but right now there's like 60-mile-an-hour winds. It's looking pretty crazy. So the height is, we're talking about Earth in feet, so we're going to go negative 16t squared. That's my gravity. That's my g part of this equation. There is no initial velocity. I'm just dropping it. But we are starting from a height of 1,353. So we got to figure out when is it going to hit the ground, aka when is h of t going to equal 0. So it's going to put this into the graphing calculator. Let's graph it. So that's 1,353. Slide him over here. And y equals, clear this out, negative 16x squared plus 1,353. Let's common sense our window a little bit. So how long is it taking to hit the ground? I don't know. We can go 0 to, we'll see if 20 seconds is long enough. Go by 2s. My y's, well, I know I'm going from a height of 1,353, so maybe I'll just go 1,500. And I want to know when it's going to hit the ground. Or actually, that's supposed to be my min. So I could do 0, but then it's going to be hard to calculate that 0. So I'm going to go negative. I'm going to go like negative a couple hundred feet just to be able to get that 0 easy. I'll go 1,500 for the height. So that's about 1,700. So I don't know, maybe we'll go by hundreds. I could do by hundreds or 200s. Good enough. Let's graph it. Boom. Perfect. So it looks like, what were my seconds? My seconds were going 0 to 20 by 2. So every dot is 2 seconds. So 2, 4, 6, 8. Looks like it's right between 8 and 10. Pretty close to 9. But let's calculate the 0. Second, calc 0, which is number 2. Left bound, well, I'm at 10. You know, you see this little at the bottom here? See this little x equals 10? That tells me where I'm at. I can see the zeros at about 9. So I got to go left. I got to come back up the curve. All right. So I hit enter for the left. Let's go down underground. Hit enter. Guess. It looks like at 9.195 seconds. So at 9.195, so roughly it's about 9.2 seconds for that penny to hit the ground from standing up there. All right, part B, and I made a mistake here on part B, so hopefully you will forgive me, but I got the wrong equation in there. Mr. Rodriguez wouldn't be happy. So the speed of a free-for-all object is modeled by the function, and it's actually the speed of an object is 32, if we're talking about feet per second. If we were doing meters, it would be 9.8. But it's 32 feet, okay, per every second, so times time. So it's basically 32t. So if you kind of made a little chart like this, you know, you'd say, okay, here's time, here's the velocity or the speed. I mean, technically velocity can be positive or negative and speed has to be positive. I'm going to kind of use them interchangeably. I'll let Mr. Rodriguez sort through all the little nuances there. But so at 1 second, the object has fell 32 feet. And at 2 seconds, it's going to be 64. And boom, 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 boom. And we want to get down to how fast is it at 9.2 seconds. So I can pretty much just put in 32 times 9.2 seconds. So notice it's picking up speed. It's getting faster and faster all the way down. So 32 times 9.2 is, so it looks like it's falling at a speed of 294.4 feet per second. You know, and every second it's getting faster and faster and faster until it gets to that point called terminal velocity. And I forgot exactly how far that was. I'd have to kind of Google it to see what terminal velocity is. But that would be our penny speed right before it hits the ground. All right, hopefully this calculator video helps you out and gets you ready for the test. See you.